Hi everyone, welcome to Coding Review Crash Course Workshop 6. This is going to be our last workshop, and we're going to go over recursion and dynamic programming. So if you look at our next slide, we have our ACM portal code, and then the slide after that is going to be a link to our slides. That is oh, there you go, and it's going to be on the screen, tinyurl /cicc-lesson-6. And yeah, let's get started. So as a quick recap, we're going to go a little bit over what recursion actually is. So basically, the concept of recursion in computer science is the idea to exploit doing a task and the same task over and over again in a way that helps you get closer to a more complicated task. So the essential idea is breaking down a bigger problem into smaller subproblems. And that's kind of how you identify where and how you can use recursion to actually solve a problem, right? So to go over stuff that like you might have gone over in class, but maybe you don't remember too well, there are like two general parts of recursion. There is the base case. So this is what you know the solution to, and this is usually the smallest subproblem. So for example, if you were trying to calculate the nth value of the Fibonacci sequence, the base case would be the smallest subproblem, so you would know absolutely the first and the second values in the Fibonacci sequence. And then the second part is the recursive call, which is what you would actually use to obtain the solution to a harder problem. And usually in a recursion problem, this is like the difficult part, right? It's easy to find the base case, but it's very hard to find a recursive call where solving a recursive problem is actually going to be good towards solving the bigger problem. And so I don't know if any of you guys have like Googled recursion, but fun fact, if you Google the word recursion, Google says like, do you mean recursion? And it links back to the same Google page that you just searched for. So it's like a fun little Easter egg.
You should also read the definition of recursion. It's I think it's pretty entertaining as well.
Oh yes, I actually didn't see that. Yeah, if you look at the definition, it says a recursive definition is the example it gives. That's pretty great. So as a warm-up, let's try to write a program to print the nth Fibonacci number. And so we won't actually be doing this. I'll just explain kind of some example code that I've written up before. But the idea is the recurrence relation for the Fibonacci sequence is going to be the nth Fibonacci sequence is equal to the nth minus 1 Fibonacci sequence number and the nth minus 2 Fibonacci number, right? So as you all know, like the fifth Fibonacci sequence number is 5 and the seventh Fibonacci number is 13. And so if you take a look at the actual code that we use to write this program, you'll see it's pretty simple. We have two areas that we went over previously about recursion. We have the base case. We know the first two, the 0th and the nth, the 0th and the first Fibonacci number, which is going to be 0 and 1. And then we have the recursive step, which is going to be the recurrence relation for Fibonacci, n equals m minus 1 plus n minus 2. But there's a slight problem here, right? What happens if you run like Fibonacci, or you call this Fibonacci function with n equals 1,000 or even n equals 50? And more related to that problem at hand, what happens when you make a recursive call in general that could cause a problem here? And feel free to unmute yourselves or type in chat if you guys know why there's a problem here. All right.
Well, each function call is going to break off into 2 separate recursive function calls. So it's going to grow exponentially. So you're going to like keep calling Fibonacci like a huge number of times just to get all the way back down to 1 and then all the way up again.
Right, yeah. So Jackson is completely correct. The problem with recursion is that the runtime of the program grows exponentially with the input n, because each time we make a call to the Fibonacci program or function, we split it off into 2 function calls. So we have effectively an exponential number of actual function calls, right? So how can we fix this? So one solution is memoization. Now, memoization is the idea that you are doing or you're doing tasks that you've already done before, or you're trying to find the solution for tasks that you've already found the solution for, right? So like noticed in this function called tree that we call the function Fibonacci2 multiple times. So the idea with memoization is if you ask the question, what if we reuse the value we had already computed, right? That would save us an entire branch of computation, and we don't have to like calculate, Fibonacci 2 again if we already calculated before. So that way we would only have to calculate each Fibonacci number at most once if we remember the last time that we called it. Now, another fun fact before we get back to memoization is the word programming in dynamic programming actually used to have nothing to do with programming, right? Because it used to be like a purely math concept, I guess. And so Richard Bellman, who developed this idea when working in like a 1950s Air Force project, he decided to use the term dynamic programming, or the term programming in the word dynamic programming, because like he thought that Congress would be more supportive of that idea of like something related to computer science or programming, rather than just like a pure math concept that congressmen might not like understand. And so even though it had nothing to do with programming before, eventually people realized that like this was an important concept in programming and in writing code. Now, we have our code with Fibonacci code with memoization. So what have we done here? Is that we have an array that's like static and global, that is like outside of our function, where we actively keep track of the previous Fibonacci numbers that we've calculated, right? But again, what happens when a recursive call is made? Like, is there still a problem here? And have we gotten rid of all the overhead with recursion? And again, feel free to unmute or type in the chat if you know the answer, or if you have any idea.
I guess now you're just computing each nth term of the Fibonacci sequence once, so you don't have all that extra work that you have to do. It's just on the order of n instead of 2 raised to the n.
Yeah, no, that's totally correct, Jackson. But there's one more problem, is that here in this code, if you look closely, we're still making n calls to a Fibonacci memoization function, right? And so usually there is some overhead related to making the function call itself. And because of that, it's better actually if we don't make n function calls, and instead we only have to make one function call, right? And so the solution to that idea is tabulation. And so usually when you normally think of the Fibonacci sequence, you don't think of it recursively, right? If you're asked to calculate the 5th Fibonacci number, you don't think, okay, so what's the 4th Fibonacci number? Okay, what's the 3rd Fibonacci number, right? You think from the bottom up. So you first take Fibonacci 0, Fibonacci 1, then Fibonacci 2, then Fibonacci 3. And so tabulation is the idea of doing this problem in a bottom-up way, right? So instead of making a function call and making recursive function calls until you get the answer, instead build your solution space sort of from the bottom up. So from your base case up until what your target Fibonacci number actually is. So here we can look at some code for our final Fibonacci solution. And basically what we're doing here is we're just tabulating the answers to the Fibonacci problem, to the Fibonacci sequence from 0 to n, and then returning the answer for n, right? So here, all we're actually doing is doing a one for loop, and we don't have to make n function calls. We just have to make one function call this time, which is, I guess, like the main. And so, again, here's another meme. Make sure you have an exit condition to your recursive functions, or yeah, I guess now that we're doing tabulation, we don't have to worry about exit conditions and base cases, but actually, I guess we still do, because it's important to have a base case, or else you have nothing to build your tabulation from bottom up. So this is still important, just maybe not as relevant in this language. Anyways, so once you guys take a quick break, drink some water, take like a 2-minute break. We'll be back at 9:21, but, or sorry, not 9:21, 6:21. But yeah, take a drink of water, and we'll be back soon. All right, awesome. Welcome back. So next, I think it's important to talk about when to use dynamic programming, right? Because we want to teach this in the context of interviewing problems. So the most important thing I think to take away from this, other than how to solve recursion and dynamic programming problems, is when you can actually use them and how to spot that, right? And so generally, there are 2 key things you want to look for when you try to spot whether or not it's a dynamic programming or recursion problem. And the first thing is optimal substructure. So it is when you're able to break your problem into smaller subproblems, and that you can combine the solutions of the subproblems to get a solution to the big problem. Right. So I know this is a pretty general, but it gets tied in with the second idea, which is overlapping problems. And so this means that when traditional approach to a problem, something like doing a brute force, using a lot of for loops, using complex data structures, requires many overlapping computations, right? And so these are like parallel to the 2 concepts we talked about before, memoization and tabulation. And so if you guys, I should probably take a step back, but if you guys didn't know what dynamic programming is, it's basically just making recursion and recursive problems that require optimal substructure and have overlapping problems more efficient. And so using those 2 concepts, you've like already learned dynamic programming, right? It's basically just building off of recursion. And so next slide, we'll have a quick summary of what dynamic programming really is. And essentially, for dynamic programming, you want to try to break down the problem into smaller subproblems that have the same structure. i.e. appear the same, but are smaller in size, right? So like finding the Fibonacci, like the 5th Fibonacci number appears the same as finding the 8th Fibonacci number in terms of the recurrence relation, but is actually smaller in size and easier to compute. The second idea is, can I go from the subproblem to the problem, right? So is there an actual relation between solving the solution to a subproblem to solving the actual problem? And then 3 is like finding an actual recurrence relation between the subproblem and the problem, i.e. the current element is somehow related to the previous elements the program has already seen. And so let's go over a quick warm-up problem before the practice problems. So for our first warm-up problem, this is actually something you've already seen before if you went to our very first lesson, where we tackled the recursive solution of this problem. But now we'll be looking at a dynamic programming perspective. So you are walking up Janus steps, which has n steps, and each time you can either climb 1 or 2 steps. And you want to find out in how many distinct ways can you climb to the top. So for example, if there are 3 steps, which is the input is the number of steps, then there are 3 distinct ways you can climb to the top, because you can either climb 1 step at a time, you can climb 1 step and then 2 steps, or you can climb 2 steps and then 1 step. So before we continue, I just want to make sure that like everyone understands like how to approach this problem in like a dynamic programming way, and like knows the core differences between recursion and dynamic programming. So I guess, I mean, if anyone's confused or like wants me to repeat any part, just like feel free to chime in, unmute, or via the text chat. But otherwise, if you have any ideas to solve this problem with dynamic programming, also feel free to speak up.
Bill, I'm gonna leave the screen up. I think if you start sharing, it'll like boot me out. So just whenever you're ready for you to share your whiteboard.
All right, yeah, for sure. Very cool. I guess it looks like all you guys have a good grasp, or at least understand how to approach this problem. And so I guess we can switch to my whiteboard while I'll go over it. So I think you can stop sharing and then I can start sharing. All right, go. Okay, cool. Can all of you see my screen? Hello, can all of you guys see my screen? Nice, nice. And it's a whiteboard, right? Like you can see steps that I've drawn here. Awesome, awesome. All right, great. So here are some like example steps I've drawn out. And the idea is you can either climb 1 step at a time, or you can climb 2 steps at a time. And you want to know how many distinct ways you can get to the top of the staircase. And so it gets pretty complex pretty quickly. Like you can, from the very bottom, you can climb to the first step or the second step, but then from the first step, you can climb like either from the first step or to the, the second step, and then from the second step, you can either climb to the third step or fourth step, and so on, right? So it gets pretty complicated. But we already know how to solve this recursively, right? So can anyone tell me, well, I guess we want to find a way that we can first represent a bigger problem and a smaller subproblem, and how we can relate those two problems together. And so does anyone have any idea of like a recurrence relation like that? Like if I asked you to find the solution for n number of steps, what can you tell me, or what recurrence solution can you demonstrate to me where solving smaller versions of this problem will help me get to a larger version of this problem? Again, feel free to unmute or speak up or type in the chat.
So, I think someone else has an answer.
Oh no, go ahead. Jackson, I mean, if you like, also share your answer as well before we get to the chat answer.
Yeah, so pretty much you can either get to the top step by going up one step or going up 2 steps at a time. So just like June said, you can either start from 1 step down or 2 steps down, and you know the total number of steps. If you know the total number of steps for n-1 and n-2, then you can just add them together.
Right, exactly. So both June and Jackson are correct. If you want to climb n steps, all you have to do is calculate the number of ways to climb to n-1 step and to n-2 step, and then add them together. Right. And so in that case, we already have our recursive solution, right? We can write a recursive problem or recursive program that helps us solve that problem, but we want to approach this with dynamic programming instead, right? So I guess let's get just some sample code written out. This one down. Okay, cool. Vectors for this. Okay, so if we were to write a recursive solution, we would write it something like this, right? So we know that if we have 0 steps, then there's like 0 different ways to get up, but if the number step is 1, then we know there is 1 way to get up. And we know that if the number of steps is 2, there are 2 ways to get up. And then we would use the recursive formula that we tried before. So otherwise, we can return num ways with num steps -1 plus num ways with num steps -2, right? And so again, we saw there were 2 problems here with all recursive solutions, is that one, because we are calculating the number of ways to get to a step each time, it means we're going to make several of the same calculation, right? We're going to calculate the number of ways to get to 3 steps multiple times if we give like a very high number. And so we want to employ memoization to solve that issue. And we also want to get rid of the many function calls we want to make. So we want to use tabulation to get rid of that other issue. And so instead of doing this, what we would introduce instead is some way to, I guess, keep this. Instead, some ways to do it from the bottom up. And so what we would do here is something like we could create a vector . let's say of size, let's see. Like this, of size of num steps plus 1. One tip that I have for all of you guys doing like DP problems while in interviews is that, I don't know, like sometimes it takes a second to figure out how large your array or your grid has to be to store your values for memoization. And so I always like to use like n plus 1 or like n plus 1 times n plus 1. That just makes like all the headaches with potentially site faults or memory issues later kind of disappear. So that's a fast tip for y'all. And so here, what should I do to the dynamic programming vector here or array here to solve this problem in a dynamic programming way? Like what should my next step be here in terms of writing code? Yeah, feel free to unmute or type in the chat. Right, so Jackson is correct. So we want to set TP0 to equal to 1. Oh, sorry. That's close to correct, I think. But I think if we want to do one step, there is one way to step up one step. And then if you want to do 2 steps, there are 2 ways to step up 2 steps, right? And we actually don't have to set the, I guess, the 0th element of our DP array because our recurrence relation doesn't involve looking at the n minus 3th step. But I guess if you really wanted to do it, you could. We've already set it to 0 when we created this vector, so that should be fine. And then, of course, the next step would be to actually implement the recurrence relation like we saw before. And so all we have to do is loop through from 0 or from 3 to the number of steps. And so at each step here, we simply apply the recurrence solution that you guys pointed out before, because we know that dpi will equal to dpi minus 1 plus dpi minus 2. And so if you look closely, this is like very, very similar to the Fibonacci sequence, right? This is basically the same thing. And so at the very end, we can return dp num steps. And so this would be our final code. That would be like dynamic programming solution. And again, it's like very similar to the Fibonacci sequence dynamic programming solution that we looked at before. But yeah, so like this is kind of how we approach dynamic programming problems. Does anyone have any questions about this or anything that they didn't understand that I would like to go over again? Okay, great. If not, I can stop sharing. And I think we will move on to our first practice problem.
Should we take a break before then?
Yeah, for sure. Let's take another like quick 2-minute break. We'll be back at 9:40. So take a quick drink of water, and we'll be back with more practice problems that are much harder than the one that we just tried, but are going to be super instructive.